Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 58, and this problem asks us to draw the stepwise mechanism for the following substitution, and also asks us to explain why 2-chloropyridine, which is our starting material, reacts faster than chlorobenzene, which is this, in this type of substitution reaction. So let's first work through the stepwise mechanism of this type of reaction, and then we'll explain why pyridine, or chloropyridine, reacts faster than chlorobenzene. So here we have an electron-poor aromatic ring, and we're reacting that with a nucleophile. Remember, sodium and your methoxy will dissociate such that your O- becomes your strong nucleophile, and then we have a good leaving group on this aromatic ring, so we can just automatically assume that we're going to have some sort of nucleophilic aromatic substitution reaction occurring. And we know that in nucleophilic aromatic substitution reaction, our nucleophile will attack the carbon that has our leaving group, being one of the halides, attached to it, making a bond. When you make a bond, you break a bond. So this pi bond will break, going on to this nitrogen atom here. So now your nitrogen atom picked up 2 extra electrons, so it's going to have a negative charge. But nitrogen is pretty electronegative, so it's okay and happy to be negatively charged like this, and it's willing to accept those electrons from this pi bond that broke. And this is actually the reason why this molecule reacts faster than chlorobenzene, because in chlorobenzene, if this methoxy were to attack this chlorine, well, then there's nothing electronegative within the benzene ring to happily accept that negative charge. What would happen is that you would form a carbanion, which isn't all that stable. You would form some sort of carbanion on this carbon, which is a lot less stable than a nitrogen with an extra lone pair electron. So this is why reacting with pyridine is faster than reacting with just a chlorobenzene, is because nitrogen is more electronegative than carbon. Therefore, it's happier to accept those 2 electrons from the pi bond, and therefore have a lower energy of intermediate state, and therefore react faster. So now continuing with the mechanism, we can show that these 2 electrons will move around the ring to make a new pi bond, making a bond. You make a bond, you break a bond. So this pi bond will move over here, kicking off this pi bond here. But now, when we make the pi bond here, we have to kick off our leaving group, so this chlorine will leave. Now we have a methoxy and sodium chloride as a byproduct.